Hello everyone, today I will present my project, which is cavity resonator. My cavity resonator is in a rectangular shape which has A, B and D lengths. I choose my A as 9.3 centimeters, 22 centimeters B, and D is 27.5 centimeters. I chose my operating frequency as 900 megahertz. For that reason, I will calculate my cutoff frequency with equation 1. I have calculated the cutoff frequency for T101 mode and it's approximately 900 megahertz. I have also calculated T011 mode cutoff frequency, which is approximately 873 megahertz. As you can see, these are my dominant frequency is T101, but T101 is much more accurate for my operating frequency. I have implemented my cavity resonator as here. I didn't wrap the outside of my cavity resonator. It's not intentional, but I bought it like that. I have wrapped inside of it by aluminum foil and put an antenna. Aluminum foil is a good conductor. Our formulas for cavity resonator is for perfect conductors, but aluminum foil is good conductor, so it's not a big deal using aluminum foil. There are surface current will occur at the boundaries, but since it's low, we can neglect that. For putting the antenna, according to our textbook, Fundamentals of Electromagnetics by David Cheng, I have to put it in the middle of the cavity resonator. The reason behind that is my E field component at T101 mode is maximum at the middle of the cavity resonator, but to prove this, I have derived the E field and H field components, but H field components are unnecessary here, but I have calculated them to show it. Here I will calculate the antenna location. This is done by just simply derivating the EY component according to Z, but since this is the maximizing this function is very simple because it's a sine function. I just maximize it by setting it to sine function's maximum value, which occurs at pi over 2. According to that, I have to put my antenna at 13.7 centimeters, which is nearly the middle of my cavity resonator. So I have proved that antenna location. Furthermore, according to our book, my antenna must be a quarter of my wavelength to receive back my E fields and transmit it. So I have calculated the wavelength by this formula and I found out that my wavelength is 0.176 meters and a quarter of it is 4.4 centimeters. So I have implemented my antennas at the middle of my cavity resonator, which is shown here. They are 4.4 centimeters. I have soldered them onto SMA connectors. These then I have uh, to better understand whether my cavity resonator is working or not. I have connect my cavity resonator by a SMA connector to network analyzer, and this is my result. As you can see, there are three minimas here, here, and here. This is my cutoff frequency for T101 mode. The others are much higher than this one. The reason behind that is the dimensions. And as you can see, my cutoff frequency is 926 megahertz, which is approximately 900 megahertz. Uh, it's good enough. Then I have plugged the SMA connector to other device and measured the input and the output voltage, which are input is 1.45 volts and the output voltage is 770 millivolts. So the attenuation is calculated and it's approximately minus 5.5 dB, which is lower than 10 dB. So it can be easily said that no need for a matching circuit, but if we want a better result, we have to match our circuit. But it's fair enough for our purpose. So I can say that my cavity resonator is working good and it's okay. So the next step, I have calculated my quality factor by this formula. This formula is just working for T101 mode, which is the mode that I am using now. The quality factor is 173.2 multiplied by 10 over 10. This is the result that we expect because cavity resonators have big quality factors. So we can say that we achieved our goal successfully. Our cavity resonator is working between 500 and 1.5 gigahertz. This is the range in the assignment. My cavity resonator is working at 900 megahertz. So that's all. Thank you for listening.